Yeah, hi everyone. Welcome to Prop Stats 5. So this one primarily in this class we'll be looking at descriptive statistics. Um, if you remember, or rather if you watched the NumPy classes, you must have seen there's something called df.describe, where it describes all the mean, median, mode, min, max values, 25th, 50th percentiles. So that is what we'll be looking at today in theory. So again, we'll be looking at measures of central tendency, which is your mean, median, mode, a little bit of weighted average, measures of variability, which is primarily range, variance, and standard deviation. And just a definition for inferential stats. We won't be looking at that in any detail today. Yeah, then a little bit about random variables. We already, if you watched the prob stats 1, which is the first probability theory, we already discussed about discrete and continuous spaces. This is something very similar, just related to random variables. Yeah, and I realized I'm not sharing the datasets, so yeah, I'll put this in the description. You can just put this in Colab. This only works in Colab. Gdown only works in Colab, so you can just paste that and get the dataset. Okay, with that said, let's begin. So basically, there are two types of you can say statistics. I don't know if there are more, but generally two types are there: descriptive and inferential. The definitions are like descriptive stats is something that describes your data. You can say it summarizes your data. Yeah, so to give you an example, if you have a speeding car, if the car is moving, you want to know the speed of this car. The speed is described in the dashboard, right? It says, let's say, maybe 60 kilometers per hour or whatever it is. So that is the description of the speed. So that is it's just describing what it's there. It's not making any conclusions, or it's not inferring anything, or it's not maybe predicting or any of such sorts. That is done in the inferential statistics part. So in inferential statistics, what happens is what it will tell is it will say in maybe if you are moving at maybe 60 kilometers per hour, you will reach your destination in 1 hour. You can make predictions, you can make conclusions about it. So that is all we'll be speaking about inferential in this class. There's nothing we'll be talking about that. Now, to just to give you an example, in inferential statistics, you will see this in action. And if you observed Google Maps, if you click on directions and you start following it, it keeps occasionally telling you expected arrival time. You'll reach in 15 minutes. You'll reach in 10 minutes. So that is the inferential in action. So let's move to the first topic in descriptive, which is our measures of central tendency. So what this means is, so there are two things in descriptive stats. One is measures of central tendency, and other is measures of variability. So measures of central tendency is nothing but you are trying to find the center of your data. So if you have a list of data points, you want to know or instead of data points, let's say, if you have a list of, let's say, heights, you want to know the center of these heights, in the sense, where is the data clustered, at which point the data is clustered. You're trying to find out that center. Suppose let's say you have 10, 15, 16, 17, 18, 20, 25, so on, so on. So if you see that the data here is clustered around this area, right? Like somewhere around here. If we to know where the clustering is, rather, if we take a graph, you will see something like a bell curve or something like this. So the data is mostly concentrated around here. So you're trying to find out that concentration point. So that is what measures of central tendency primarily finds out. You can find the center using mean, median, and mode. You can even find that through weighted average, although we'll look at weighted average. You can use weighted average for both descriptive and inferential as well, but in this class we'll be looking at it in the descriptive measure, like it simply is there to summarize our data. So that is about measures of central tendency. Measures of variability is you are trying to find out what is the spread of the data around that center. So once we find the center in central tendency, variability will tell us how far away the data points are from the center that we found. Center could be mean. So there are so if you see variance and standard deviation. So we have range, variance, and standard deviation. And in range you have IQR as well. So basically these three, range, variance, and standard deviation. So these three help us find the spread of the data. Now variance and standard deviation use mean as the center, while range and IQR do not use anything. There are other measures of variability as well, I think. They use some other centers, like some other ones could use median. Actually, median, I think IQR uses median. IQR uses median. IQR uses median, and maybe some other measure could use mode as the center. So the idea is to find the spread of the data. Like if I take this graph itself, how far away the data points are spread from the mean, right? These data points. Basically that's the the definition for measures of variability. And one might ask, like, what is the use of finding the central tendencies and variability? Like, what is the use of finding the spread? So we like central tendency, like I said, it is meant to find you can say the typical value of any data set. Like, let's say I have the list of heights for a particular city. Now you want to know, like, what is the typical height, average height of a citizen in this city. That is where you can find out using mean, something like using these central tendency methods. You can find the typical values, and variability is for something like let's say you have two machines which are making bolts. Let's say it's making bolts for iPhones. Now you want to know which one is more precise, right? That precision value is you can find out using variance. If the variance is rather using measures of variability. If the variability is lower, it means it's more precise. If it's higher, it means it's less precise. So you can also compare the performance of different batsmen. That's the example we'll be looking at in the IQR case study here between Rahul Dravid and Sehwag. So we want to know, like, who is more consistent. Yeah, this is the keyword. It's about finding the most consistent system, the more stable system. Variance informs us which system is more. Like, suppose if you want to know what is the income of citizens across a country per month, right? You can use variance for that as well. Like, how far away they are from a typical salary person in that country, right? You can also find out, like we also already used the height example, right? What is the typical height of a citizen in a country, and how far away they are from the typical, like how far away is a citizen in the far corners of a country. How is he from the typical height that we have measured? Or we can also find out the customer satisfaction levels using measures of variabilities. Like suppose so a customer service guy did maybe let's say 100 calls, and in these 100 calls the customers gave the ratings. So how consistently he got rated a particular value, or rather how you can find out his performance. This will become more clear once we do the case study. So that's these are common use cases of measures of variability, measures of central tendency. Now let's begin with the first topic in central tendency. Yeah, let's take the sample salaries. 30, 35, 40, 40. So here the question is, we have so the HR is looking at bunch of salaries for let's say a software engineer, okay, in a big tech company, and they the person found out that these are the average salaries that the candidates were getting, and if he now the HR wants to hire a new person and wants to negotiate the salaries with him or her, then the salary should fall, the HR would expect the salary would be somewhere within this range, right? So we'll look at mean. So mean is nothing but sum of terms by number of terms. This is we already learned this in when we were in schools or something. Sum of terms by number of terms. Basically, you can find the central value using this method. So the formula would be sigma equal to 1 to n. Sum of the terms would be x by n, xi by n. So in this case, okay, let me write this properly. The mean is defined using this Greek letter mu equal to sigma equal to 1 to n x by n, where mu is the population mean. Just think of it as mean. Xi, I'm sure you know what sigma equal to 1 to n means. It just means that we are summing all the values. Let's say we have something like, let's call this 30, 30, 35 as x1, x2, x3, x4. So instead of writing all this, we use this shorthand to express this one. So x is the individual element, or rather in this case the salary of a person, and n is the total number of terms, or total number of values in the salary data set. Yeah, I hope that was clear. I feel like I'm missing something, but yeah, let's calculate the mean. So here mean would be sum of terms. Here that would be 30 plus 30 plus 35 plus 40 plus 40 by 1, 2, 3, 4, 5. So how much is it? 60, 95, 135, 175 by 5. 5 3s, 5 5s, 25. So average is 35. It seems kind of correct, right? So this is how we found the center of this data set. Now the problem is, in big tech companies, like the salaries can vary vastly based on skill set, based on previous maybe it could be a startup acquisition. They did an acqui-hire, or recently you heard Meta giving hundreds of millions of dollars, right? So the salaries could vary. Like suppose you have maybe somebody got somebody has a 100 lakh, and somebody has 200 lakh as the salary. Now if we calculate the mean, that would be 175, 275, 475. So that would be 475 by 5. That would be what? 5 9s 45, 5 5s. So now the mean became 95 lakhs. So what this means is, now the HR will falsely think that the mean, or rather the average salary that the new candidate can expect can be within 95, like up to 95 lakhs the candidate can negotiate, which is which is incorrect basically. So from this we can conclude that mean is not exactly good for mean is not exactly robust. Like it does not give us accurate center when there are outliers in the data set, right? You can use mean when there is like when the data set is very symmetric, in the sense that there are no outliers, there are no like extreme values in the data set, and and all of them have equal importance. We will understand this importance part in the weighted average, but yeah, just think of it that way. For now, just think that when the data set does not have extreme values, we can use mean. Now, what to do in this case? So this is where when there are extreme values, this is where we use median. Right? So median is nothing but it is the middle value. To put it bluntly, it is the middle value of a sorted data set. So right now, we fortunately have this data set sorted, but the important thing is first sort the data, find middle value. So what we will do is, we'll take the above example, 30, 30, 35, 40, 40, 100, 200. So what would be the middle value in this one? So the data set is sorted already, right? Sorted, it's already in the ascending sort. So the middle value here would be, how many are there? 1, 2, 3, 4, 5, 6, 7. So 7 are there. So the mid value here is 40, right? So in this way, now the HR knows that 40 LPA is like the average expected value that the new candidate can negotiate up to. Like they can negotiate around this range. But so how do we find this? Now this is like we just counted and found this. So but how do we find this in like if there are like 10,000 records or something? We cannot go through each and every record, right? So For that, we use a simple formula, which is if the number of records are even, or let's go with odd first. If the number of records are odd, then we simply use n by 2 plus 1th term. Which is our middle value. So if we see here, what is the total number of elements are n. So n by 2 would be 1, 2, 3, 4, 5, 6, 7. N by 2 would be what? 7 by 2 is somewhere around 3.5. 1, 2, 3, 4, 5, 6, 7. Yeah, so n by 2 would be 3.5. So plus 1th term. So we will use this is the third, plus 1th term is 40, right? So that's how you find the middle value for this one. For odd numbers, if the records are even, then middle value will be the mean of these two. Okay, since we have colors, we can use colors. Let me use colors. So we will use the mean of the middle two values. So even number, sorry, is it this one? Okay, let's say there is another value called 300. So now we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 values, right, in this data set. So we will take the middle two values and get the mean of these two. So the formula then would be, which is what? We want this term, which is this one, we will use n by 2 plus 1. Then, no, this is not this one, wait. Here n by 2 would be 4 by 2, sorry, 8 by 2 would be 4, right? 0, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. Okay, so n by 2 would be 4. Okay, this would be fifth term. This is 5th term, not this one. So the 5th term we'll get by n by 2 plus 1. The 4th term we will get using n by 2 alone. So n by 2th term and n by 2 plus 1th term by 2. So we get the mean of the middle two values if the data set has even number of values. So let's calculate even first. Let's say this is even. In the even scenario, what would be the median? The median would be 40 plus 40, which is 80 by 2, 40, right? In the odd scenario, we'll get rid of the 8th term. So only 7 of them. So in this case, the middle value is clearly n by 2 plus 1th term, which is 7 by 2 plus 1, which would be this 40 alone. So in this case, 7 by 2 plus 1, we'll round off to 3's. 3 plus 1 would be 4th term, which is our 40. So in this case also it's 40, but yeah, maybe we can make this as 45. No, you get the idea anyway. Or rather, maybe let me just change this to 40. Okay, let me change this to 50. So in this case, so this remains the same. The even will then become 50 plus 40, which is 90 by 2, which is 45. Right, so that's how you find the median. And this, as you can see, this is far more robust to, not far more, this is actually pretty robust to outliers. If you see the mean gave us 95, while median gave us the much more accurate average of 40, much more accurate center point, much more accurate middle value of around 45 or 40 depending on the data set. And this one is irrespective. This could even be 10,000 as well. Maybe somebody got 10 crores or something like that as well. It is still you will still get the accurate average. But if you look at mean, I mean, imagine if there were like 10,000 here, this will just blow up disproportionately. So that is the advantage of mean. Coming to median, we covered mean, median. Now let's go to the mode. The third one. So mode is primarily used for categorical data, not for numerical data. So this is for finding. You can even use it for numbers as well, but generally it is used for categorical data. Like you want to find out the most popular product. So the definition of mode is basically the most frequently occurring element in the data set, right? The element with the highest frequency. So if you have a data set like, we take the same example, 30. Okay, let's not take the same example. This thing has, we can take the same example later on. So let's say I have 30, 40, 50, 50, 50, 60. So in this data set, if you see what is the most frequently occurring element, which is 50, right? This came 3 times. So the mode would be 50 here. Right? If suppose okay, I'm not following the missed weighted average. Yeah, we'll cover weighted average. So if suppose the data set contains everything is unique in the data set. Suppose the data set is 30, 40, 50, 60. What is the mode here? There is no mode here. There is right. This in this case everything has a unique value. So there's no mode here. And if suppose in our same above data set, if we take 30, 30, 35, 40, 40. So here we have 2 frequently occurring elements, which is 30 and 40, right? So the mode here is bimodal. It's called bimodal, and this is part of the multimodal scenario where multiple elements are frequently occurring. So we use mode to find out something like if you want to know like the most popular product in your catalog, in your company, or you want to find out the that's the thing, that's the idea. You want to find out the most frequently occurring element within that data set. So that's the idea there. I don't think I'm missing anything. Anyway, let's move on. I forgot weighted average, so we'll do weighted average. The other type is weighted average. So weighted average is a scenario where every data point has an importance or relevance attached to it. So this is, suppose you have a list of subjects that you are the best example is the GPA. Like in your college, you have grade point average, right? Like you have studied several subjects, and not all subjects have equal weightage, right? Like maybe you studied some a subject called moral values, and there there is another physics subject, there is another chemistry, and maybe you did some extracurricular activities, right? So let's just name them. So extra, then physics, chemistry, and math, and let's say moral, right? These are the subjects, and each subject has a grade and respective marks that you scored. So let's say extracurricular has 1 grade, physics has 5, chemistry has 5, math has 5, and moral has like maybe 2. Suppose it's just assume, okay, let's take this as 2 and this as 3, and you scored some marks out of 100, like maybe you scored maybe you scored 100 for this one, and you scored maybe 60 here, maybe about 70 here, maybe about let's take easy values. Let's take about 60 here, and you got maybe 90 here. So as you can see, all subjects are not same. Let's say the importance of each subject is different. So in this case, to find out the mean, what we do is we multiply each marks by its weightage, by its importance. So the definition is basically the sum of each element, or rather the sum of the product of each element and its weight divided by the total number of divided by the total of the weights. So the formula would be something like weighted average will be sum of I equal to 1 to n. That will be your weight times each element divided by 1 to n sum of weights, right? So if we translate this in the above, I mean using the above dataset, we will have something like so weight times the marks would be 2 into 100 plus 5 into 60 plus 5 into 70 plus 5 into 60 plus 3 into 90, right? What would this be, like 200 plus 5 6 are 300 plus 35 plus 300 plus 270 over sum of the weights. So we want to add all these weights, which would be 10, 15, 17 and 20. That's a nice 20 there. So solving this will give us our weighted average, which is 500, 800, 800, 1150 and 1150, 1350, 1420 over 20. So that would be 2 sevens, 2 ones. The weighted average is 71. Right? So that is how you solve this one. There are equivalent NumPy methods for mean, median, mode. I'm pretty sure we saw this in the NumPy section or NumPy Pandas section. We'll do that as and when we solve the problems. But yeah, this is the theory part, so I hope that was clear. I don't think I'm missing anything. So we have when we look at variance, I think we'll have a data set. Yeah, nothing here. Yep, that's all there is to central tendency. Yeah, if I miss anything, I will cover it in another class anyway. So yeah, now let's move on to measures of variability. As I said in the beginning, variability is nothing but we are trying to find the spread of data around the center, around the central tendency, which is the center, could be mean, median, whatever, right? So if you look at the first one, and by the way, spread, I think I don't know if I said it, but spread is the distance of a data point from the mean. From the mean, like how far away these data points are from the mean, or not the mean, from the center value, could be mean or median or whatever, right? So we'll look at the first one, which is range. Range is nothing but max minus min, right? Max minus min, which is the maximum data point minus the minimum data point value. So if we take the above data set here, 30, 30, 40, 35, 40. So here max would be 40 minus 30, that is 10. So range is 10. So the spread of the data points is around 10 from the center. In this case, it's not situated to any particular thing. It could be anything in general, any central tendency in general. But this range has the same problem as mean. So suppose if in the data set, like if in our above data set, say 30, 30, 35, 40, 40, if we have 100 and 200. Now if we take the min, max minus min, what is the max value is 200, right? And min value is 30. Now the range became 170, right? Pretty messed up here. So as you can see, range is also susceptible to outliers. It gets highly affected by outliers. So in order to tackle this one, or rather in order to correct this, or rather in order to handle data sets where outliers exist, which is most of the data sets, because real world is always messy, we use something called IQR, which is interquartile range. Interquartile range. So what this does is, it's actually easier to explain with a box plot, but basically it takes the median. Again, the solution is using the median. It separates the data set into 4 parts using quartiles. So it divides into, it creates 3 divisions, which is Q1, Q2, Q3, which is it divides the data set at 25th percentile, 50th percentile, and 75th percentile. We'll see what percentile is. Basically, okay, why am I just saying it? Let me show you. Okay, so IQR is, it divides the data set into four equal parts, Q1, Q2, Q3, which is our 25th percentile, 50th percentile and 75th percentile. And what it does is it subtracts Q3 minus Q1. That's the formula. IQR is nothing but it separates the Q3 value, it is the 75th percentile value, from the 25th percentile value to get the proper range. And these are nothing but medians. So this data set is first the median value is taken, this Q2 is the median. And within these two halves, there is another median taken in the first half and another in the second half. So that's how the data set is divided into. Now coming to percentile, 25th percentile means 25% of data is below this value. So let's say if I say 25th percentile value is maybe 30, right? So then 25% of values, right, are below number 30. To give you a much more real world example, let's say I am in the 95th percentile in my class. What this means is I am better than 95% of the people in my class. This in fact this is the best measure of you can say this is the best way to measure somebody, because in many schools and colleges some teachers like give marks left, right and center, and some of them are very stingy with numbers. So if I said like I got 95 marks in let's say physics or chemistry or maths or something, it might not be as useful compared to me saying I got 95th, I'm like the 95th percentile in my class. Because there could be like, maybe, who knows, maybe this teacher was weird and and was liberal with marks and gave like 95 marks, like greater than 90 or 95 to a lot of people. And you, in that case, you might be like somewhere among the masses and not necessarily like you are not competitive enough. So to know like if you are competitive enough, this is a better measure. Percentiles are better measure. It's basically a ranking kind of thing. So that's the thing. If I said like in using the above example here, if I say 50th percentile is somewhere around 60. So what that means is 50% of the data points are less than the value 60. Right? If I say 75th percentile is around 80, the value is 80 for Q3, 75th percentile, it means 75% of the data points have value less than 80. So that's what it means. Yeah, I hope that was clear. That's all there is to percentiles. Nothing too fancy there. Let's visualize this using a box plot. We already saw this if you watched the data visualization section in the previous classes. I discussed box plot quite elaborately, I think. But yeah, let me give you some theory on how it is actually setting the values. We already saw it. It's all based on medians, but there's slightly more than just medians. Like, how does it decide which values are outliers and which values are actually the data points falling within the IQR range? Like, how is it setting the IQR? How is it deciding the edges? Like, what is the range of this data set, and what goes beyond that range is considered, like what is considered an outlier. We'll see that. So suppose we have some data points like let's say 1, 15, 16, 17, 17, 18, 20, 25, 25, and maybe let's say 100, 200, 250, 255. Okay, so these are some let's call this as let's call this as scores of a game. Let's call it game scores. Now if I want to plot this, so let's take the normal range here. Normal range is max minus min, which is basically 250. What is this? 255. Is it 255? Yeah, I think it's 255 minus min is 1. So 254 is the range. But is that the correct range of this data set? That's what we want to find out. Actually, let's remove 255. Let's keep 250. So 250 minus 1, 249. Let's keep it 249. Well, let's remove 250 as well. Let's keep it as 100 and 200. So this will be 200 minus 1, 199. Right? Now, if I want to find out the correct range, I need to find out the IQR, right? IQR is Q3 minus Q1. How do I get the Q3 value? So suppose this is the box plot is something like this. The box itself, in box plot, the box itself is the IQR. This is the Q1 and this is Q3. So the Q1 to Q3 is the box range. The line is the median, which is basically the median value, which is our Q2. This is the 50th percentile value, this is 25th percentile, and this is 75th percentile. What else? And then there are the whiskers, which define the range of accepted range of this dataset. Like it is saying, like until here the dataset is normal. Beyond this, it's abnormal. If there are values beyond this bands, then they are called outliers. These are outliers. Also outliers, right? And so how are these edges decided? These are decided based on a calculation. This is something that statisticians came up with, I think, after a lot of repetitions, a lot of experimentation. For the lower half, the lower range, or rather the lower limit will be, it's called, it is defined by Q1, which is this one, Q1, which is our 25th percentile, minus 1.5 times IQR. Why 1.5 and all that? That is again, that's the number that statisticians came up with after trial and error. This is just something that you have to remember. There are some things in like statistics that you will see. There are some fixed accepted values that everybody uses, like in when taking sample sizes and all, they will say minimum 30 samples. What is that 30? That's just these are just like some standard values that we use. This is something like, again, statisticians came up with after a lot of experimentations. Everybody decided that these are the these are the, like you could say, standard numbers. So to find the lower value, we use this formula, and to find the upper value, we use Q3 plus 1.5 times IQR. Right? These are the, this is how we find out. This is how the box plot is defined. Now let's try to find out these values manually. So we have our data set. Let's take our data set. So this is our data set. Now, if we want to find out, for the first thing we have to do is find Q2, which is our median. How do we find median? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 terms, which is very nice. So all we have to do is find the middle value, which is 1, 2, 3, 4, 5. In this case, it would be 6th. N plus 1 by 2, right? Right? Is it n? Oh, yeah. I think it is n plus 1 by 2. Okay, wait. 11 plus 1, 12. Yeah. Oh, sorry. It was n plus 1 by 2, not n by 2 plus 1. Where was it? Yeah, here it's not n by 2 plus 1, it is n plus 1 by 2. So that would, I was thinking something is wrong here. So that is the one. So if you have odd number of elements, so like if you have seven values here, so if you have 7 elements, you do a 7 plus 1 by 2, which is 8 by 2, that is 4. So fourth, 1, 2, 3, 4. 40 is the fourth value. So yeah, my bad. I think I got confused there. So since there are 11 elements here, 11 elements, that would be 11 plus 1 by 2, that is 12 by 2, 6. So 1, 2, 3, 4, 5, 6. So 18 is the 6th value, and so our median is 18. So when we define the box plot, the middle value is 18, right? So now we want to find the median for this half of the first half of the data set, which is this one, and the next half of the data set, this one. So we'll find median between these two. So 1, 2, 3, 4, 5. So we have 5 elements here. So 5 plus 1 by 2, 6 by 2, which is 3. So the median for this will be 16. And we can just see directly here, the median for this will be 25. Here also 1, 2, 3, 4, 5, right? 5 plus 1 by 2, 6 by 2 is 3. So this will be the 1, 2, 3, third element. So Q2, Q1 is 16. Q1 is 16. Q2 is, this is Q2, so this is Q3. Q3 is 25. Q2 is 18. So you see here, immediately you will see the range is very different. So what is our IQR? Q3 minus Q1, which is 25 minus 16. 25 minus 16 is what? 4, 9, right? So our IQR is giving 9, while what is our range giving? The range is giving 199. So you see the difference. So that is how IQR again is more robust to outliers than range. Just like median is more robust to outliers than mean. And this this variability thing uses median to tackle outliers. So that's how you find the IQR. Now, since we do have IQR, we can find the edges, right? How do we find the edges? Like I said, the formula for edges is the lower edge is Q1 minus 1.5 times IQR, right? So what is Q1? Q1 is 16 minus 1.5 times IQR is, we know here it's 9. So that would come out to be 0.5 times 9 is 13.5. So 16 minus 13.5, 14.5, 2.5, right? So the lower limit is 2.5. Now let's find the upper limit. The upper limit is Q3 plus 1.5 times IQR. So this will be, what is Q3? Q3 is 25 plus 1.5 times IQR is 9. We already know this one. It is this came to 13, right? 13.5. 1.5 times 9 is 13.5. So 25 minus 13.5 is 11.5. So we saw here. So we know the upper limit is 11.5. So anything beyond these values is an outlier. So from this one, we can see that in this case, what are the outliers here? 1 is an outlier, right? Since it's below 2.5, and our max is 11.5. Oh, wait. Something's wrong. Oh, sorry. What did I do? So 30. Okay. It should be 25 plus 13.5. I think I subtracted. Yeah, it's 38.5. This should be 38.5. Why did I subtract it? 38.5. Okay. That's correct, right? So 9 into 1.5 is 13.5 plus, yeah, that's correct. So anything beyond 38.5 value is an outlier. So in this case, this is valid, this is 25 is valid, 25 is valid, 100 is way beyond 38.5, right? 200 is again way beyond 38.5. So that is how you get 100 and 200 as outliers, and here you will get 1 as outlier. So that is the that's how you compute, or rather that's how box plot is constructed. I think we covered everything here. Yeah. Yes, I think we covered everything. Let's go to the next topic, which is variance. So, again, the definition for variance, standard deviation, they are all the same. We are just trying to find the spread of the data. The difference is the variance, like rather of course the difference is in the units. So variance, we will get the units in squared units, and standard deviation we'll get it in the normal the units that the data set already has. So if the units are in centimeter square, if the units are centimeters, then the variance will be in centimeter square, and the standard deviation will be back to centimeters. The proper definition is the definition of the formula. So let's do the formula and then construct the definition. Yeah, I guess here we'll have to use the dataset. So we'll use the dataset. The dataset is this one, weight-height.csv. You just have to copy this gdown thing. Oh wait, something's weird. Interesting. Okay. Okay, it copied everything. So all you have to do is run this. That will load the dataset into your. That will import the dataset here. So you see this weight-height dataset. Now I'm not sure if I have everything, but let's see. Import pip install pandas numpy matplotlib c1. So we'll be doing some plotting as well. So let's just see if everything's there. I think everything is there. Import numpy as np. Import pandas as pd. Import matplotlib dot pyplot as plt. Import cpon as sns. Now we'll import our we'll see our dataset. We'll look at our the overview, which is df equal to pd dot read csv weight height dot csv. So this is our weight height dataset. Now let's look at the descriptive statistics. df dot describe. So this describe method will give us conveniently all the descriptive stats, which is our mean. So we saw mean, right? We'll be looking at standard deviation anyway. You know, we'll get the min, max, and we get the percentiles, right? Now let's plot the let's do a hist plot here. We'll do a hist plot or a no, we'll do a box plot. Yeah, box plot. Yeah. Hist plot will be doing that for the IQR study anyway. Wait a second. No. We'll be doing the hist plot only. SNS dot hist plot. Yeah, and by the way, we are focused on the heights. Let's look at the heights for now. So let's look at the descriptive stats of heights at HEIGHT. So these are the stats for the height column. I will plot the height histogram just to see the what variance means, or rather how spread can be visualized. By the way, box plot is used for visualizing the spread and distribution of the data set. We'll just drop the data here as df and xy. I think any one of these should be sufficient. With x, let's put x as the height. Okay, that worked. So as you can see, this is the spread of the data set. So as you can see, the most of the data is concentrated in this area here. Somewhere around, I think the mean would be somewhere around 65, 67-ish, 67, 68-ish, somewhere over here, right? And the spread is something like this. Now, how do we get a numerical value of spread? To get it more accurately, we will use a small guessing game where we will try to guess the height of the person, and then subtract the guessed height from the from each of the data point. The guessed height should ideally be mean, because the mean is what describes it's what summarizes the entire data set. So again, I think the best way to do it is, if we want to say these are all heights, right? So these are all heights. So let's say we have h1, h2, h3, h4 as the heights, suppose, and I want to subtract the heights from the mean from this one, because mean is the ideal height of, or rather mean is what summarizes this data set, right? So if I do this, like suppose if the height is 65 and mean is 68, I will get 3. If the height is 70 and the mean is 68, I will get -3, right? If the height is 30 and the mean is 68, I will get height as minus. I'll get the spread as -38. So we don't, and if it is greater, we will get it as something like 2. So in order to, and if the height is exactly the same, then the value will be 0. Oh, sorry. Yeah, then the value will be 0. Excuse me. So I was saying the height h1, h2, h3, h4, and we are trying to subtract from the mean. Here we assumed mean is 68. If I'm trying to, we are playing a guessing game of the height. Now the guessed height can be like vastly different. So the best way to like estimate the average height, rather the average height is the mean, right? So that's the best summary with the least amount of error we can get. So if we try to find the variance, we are getting negative zeros and positive values. Now this is not very convenient. In fact, negatives are also not, negative variance is also not useful. So in order to handle these negative values and make the math more convenient, what we do is we do h minus mu, we square it, so that we cancel out the negative values, and also this process makes the algebra more convenient. We could take a modulus as well. We could take a cube or whatever, but cube does not handle the negatives, and modulus actually makes the math slightly more complicated. So in order to make things easier, we just take a square here. We square each and every estimate here, and what we do is we take a mean, which is basically we calculate each and every thing, and we take a mean of all this. So we say something like h1 minus mu whole square plus h2 minus mu whole square plus so on, something like hn minus mu whole square. by the number of terms. This will give us the sigma square, which is our variance. Now, since again writing all this is tedious, so we take a short form, sigma equal to 1 to n. Give me a moment. 1 to n hi, which is our data point I, which is our heights. In this case, we can even call it xi just to make it more general. The x is the h here, and minus mu. Mu is our mean whole square over n. N is the number of data points in this game or in this data set anyway. This sigma square is the variance. N is the total number of elements. Mu is the mean, and xi is the each data point in the data set. Again, we use summation to sum all this. So let's say the data points are 10, maybe 11, or let's make it easier, 15 or something like this. So the calculation will be something like 10 minus, so the average will be what, 15, 25. Let's make it easier. Let's make this 15. Let's make this 20. 20, 35, 45. Right? So 45 by 3. Okay, this is not easy. Let's make this as, don't want to calculate all this. So let's make this as 5, 10, 15, 20. Okay, 20, and let's take 25 one more. So the mean here is 25, 45, 50, 60, 70, 75 by 5, which is 5 ones, 5 5s 25. So the mean is mu is 15, right? So 10 minus 15. Oh, I actually made it complicated. Okay. Okay, I actually made it complicated. So let's take 3 only. So this is just a random data set. We are taking 3 elements. What is the mean here? For 15, 25, 30. Yeah, 30 by 3. This is nice. So we have mu as 10, right? Now the calculation will be 10 minus 15, or rather 5 minus 15 whole square plus 10 minus 15. Oh, something's happening. 10 minus 15 whole square plus 15 minus 15 whole square by 3. This, we calculate this one, which is 5 minus 15, so this is 10 square 100 plus 10 minus, so this is 5 square 25 plus 15 minus 15, that will be 0 by 3. So this will be 125 by 3, 3 fours, 3 1 point something. So let's say 1.6 40. So this will come to 41.6. So variance here is sigma square is 41.6. So this is the spread of the data. Again, range, variance, standard deviation, these are all different ways of measuring spread of the data, each used for different scenarios. So they are all essentially the same with slight unit differences. And this one, so this one, if this was in centimeters, it would be centimeter square, right? Now what is standard deviation? Standard deviation is nothing but sigma is square root sigma square, standard deviation. So it is nothing but sigma. Sigma is the standard deviation, right? it is the square root of variance. Variance is sigma square. So square root of sigma square is sigma, right? That is the variance. That is all there is to it. So now the units will be centimeters, which is back to the standard units that the table has. Yeah, so as you can see, the more commonly used one is standard deviation, something that we use to communicate to humans, or generally that which we perform. Variance is used in different statistical methods, like if you have something we'll see in the future classes in hypothesis testing and all that stuff. There's something called ANOVA test and regression, and in different other statistical procedures we use variance. So like in those scenarios, sigma square is more convenient. But generally, when we are talking to humans, or when we are trying to find what is more consistent, in that scenarios we will see standard deviation as the more used one. It's something that we use to communicate. That is what we use to communicate. So that is about standard deviation. Now let's look at the case study. There's not. I don't think there is nothing much to say here. So if I have to say the definition from the equations, what we can say is variance is the mean squared spread of data. That's the definition. It is the mean average squared spread of the data set, while standard deviation is the average spread of the data set around the mean. So these are, again, like I said, variance and standard deviation both revolve around the center, which is mean, particularly. I guess that's it. I don't think there's anything more to discuss here. Let's go to the case study. Let's go to the case study. I think that's it. This is the case study where we are trying to find out which batsman is more consistent. In this case, we are looking at the runs of two cricketers, which is Rahul Dravid and Sehwag. If you are familiar with cricket, like you will know that it is said that Rahul Dravid is the more methodical, like more systematic player, while Sehwag is more aggressive player, right? So in this, in this data set, we are trying to find out if, suppose, we have a match and like India has a match with another team, and it needs 30 runs, let's say, to maybe win the match. So whom will we choose? Of course, it depends on the number of balls that are available, that are left, and also the run rate and all that stuff. But in general, we want to choose somebody who can reliably give us a certain number of values every time, like who reliably produces a consistent number of runs in every single one of his match. So in this in these two datasets, we have two datasets. We'll be looking at those two, and we'll finally conclude who is the more consistent player, right? So yeah, we'll now load the other two datasets, which is the first we'll look at the sehwag's dataset. Now let us load the dataset df equal to dravid.csv. So you see here we got the dataset here sehwag.csv f.head. Yeah, now we have to do some cleaning here because as you can see there are some unwanted values in the table, and also if we look at the info, if we look at the type of the columns, they are also not convenient. Actually, we don't need all of them, so we don't have to convert each and every one of them, but we'll do it anyway. So if you see here, all of them are of the type objects, which clearly it's not convenient for us to do any numerical operations. So we'll have to convert the objects to appropriate floats and int types, and then also we'll have to drop these. We'll have to first clean this numerical some of the numerical columns. If there are any infinities, we have to get rid of them. So we'll do all that quickly. So first let's look at the data set. There's actually some unwanted things here. So if you see here in this numerical column, there are stars as well, right? So first we'll have to get rid of those stars. So df, okay, let's not call it df. Yeah, actually we can call it df anyway, since we are going in sequence. At the end we will simply be comparing, so that's fine. So df, this is our runs. So from this runs, I want to remove .str. We are calling the string object, and we are performing the replace operation. I will replace all the stars with empty. So I'm just trimming those star values from this column. Now if we check df head, it should ideally remove that. So that removed the stars from it. Now what we want to do is we will get rid of all the D and B values. And in fact, if you look at the there is another, I already looked at this dataset, so I know there is another string value which is not desirable. In fact, if you look at there is something called TD and B as well. So we want to get rid of TD and B and TD and B and what else? And D and B. We want to get rid of these two values. So what we can do is, first of all, we have to find the indices that these values that this column has with these values. So indices equal to df dot, is it pd dot index or df dot index? 1 second. Okay, it is df dot index. So Yeah, if I'm not wrong, I think we can use dot str dot no. So we are trying to find what I'm trying to find. Okay, we'll use a mask here, and let's see what it is. So tf runs dot str dot contains. Yeah. So contains. We are trying to see if it contains either this or this one. We want all the indices of these two particular values. So any rows in this runs column that have this TNB and TDNB as values. Let's see if this actually gives us. Nope. Object is not callable. I think it is square brackets. Yeah, so it is square brackets. So so these are the indices where this TDNB and DNB exist. So what we will do is drop the indices, drop the rows with these indices. So all we'll do is df.drop. If this takes in labels is the list of labels, which is our indices. Okay, let's assign this. So those are our indices, and and we'll set the axis as well. I think the axis is default 0, but we'll put it anyway. Axis is 0, and you know 0 is the so one is for the columns and 0 is for the so 0 is for the index. So you see here, that's the documentation, and we will do an in place because we want to modify the existing dataset. So we'll do an in place equal to true. Now if we see the data set, say top 20, you can see here the values are gone, right? So you see here there is a DNB in the first index and in the fourth index. That stuff is now gone here, right? Now now what we want to do is we will convert all the necessary object types to integers and floats respectively. And the best way to approach this is to first of all convert all the integer types to float values, and then handle the nans and infinities in the floats, set them to 0, and then convert them to type int, those columns. So in this case, let's take our list of columns that we want as floats. So the first one will be, excuse me, the first one will be runs, obviously. Then we'll do mins, we'll do ef. We will only be using the runs column, but this is just like an exercise for you and for me as well, just to brush up my memory. SR, we will take the positions as well, and we'll take the ins as well. So these are the numeric columns that we want to convert to. We can obviously do date time conversion and stuff, but we can see that some other time. That's something we will not be using it here. So anyway, and if you see here, SR is already a float type, but the rest of them are numeric types. So we'll put this at the end and we'll reuse it separately. So what we can do is we will iterate over each and every one of these columns. So for column in columns, right, I will do a pd dot to numeric df column, which is our column that I'm getting from here. I will reassign this column after I convert the column to numeric column type. Df okay, it is, I think, pd dot to numeric. One second, let me check the documentation. Scalar list tuple. Okay, so it accepts the series directly, so we'll pass the series. So df call, you see here this argument accepts the series, and we will errors will do a course. If there are any issues when it converts the column from object type to float type, it will raise an error. We want to handle the errors we want to coerce the errors, which is basically coercion is, let me see, one second. Any errors raised during the downcasting will be surfaced regardless of the value of errors input. Wait, one second. Yeah, raise an exception. If coerced, then invalid parsing will be set as NaN. So that's what we want, right? If there are any issues, then just set the value as a null value. So errors equals, we will set it to coerce, and now let's see the yep, that's it. That should convert all the data types. So let's look at the data types. You see here, okay, it surprisingly handled these two int values as well. Actually, that's convenient. This is exactly what we want, which okay, so that automatically converted those values to int64. So we don't have to do a second pass where I have to set it as type to int. So that is that's good. We don't have to do anything. Df dot we already have the data ready. Although this we want it in ints. I guess we can convert that one thing to ints, and rest of them look pretty fine actually. This is the float value, which is the SR. SR should be float, but mins should not be float. So what we will do is we'll try to force df mins equals dot as type. Let's see what happens. Nope, cannot convert, non-finite value. So there are some infinite values somewhere in between. So we cannot do this directly. So what we have to do is first we'll have to let's see. First we'll replace np.inf and minus np.inf with np.nan. So we'll replace all infinities with null values. Then okay, I think I have to do an as type int as well. Let's see. df.head okay. Now we will convert this to type int as typeit. Okay, 1 second. Cannot convert. Okay, I think I have to do as type. Oh, okay. No. So the next step is we want to set the fill all the nan values as 0. Then what we can do is we will convert the types to int as type. Hopefully that works, and I think that worked. So if you look at the df info, there you go. That's our int value. So if you look at the data now, you will see the mins is also ints. So that is our data preparation. Now let's look at the actual thing. So we have our data. What we want to do, we want to analyze the runs. So we'll just use the runs column. So these are the runs of sehwag. Actually, we might want to keep this as a separate thing. So sehwag, let's store it as a separate column, so that because we'll be computing standard deviation and we'll be comparing, right? So I think it's better to keep it separate anyway, because yeah, let's give it a separate name, so that the next data set will have dravid as the variable name. So yeah, now the quickest way to visualize this is obviously to plot it. So let's just plot it and see how the IQR and all that stuff are. So sns.boxplot, see the documentation once, what it takes. Data is our sehwag, and the columns obviously we'll have to define. I don't think we have to define a column, since it is the oh, wait a second, I think this is series. Data is series. There you go. That's our box plot. Let's flip it once. There should be an orientation somewhere. Yeah, orient. What does orient take? So this is vertical, I think. So we'll flip it to horizontal. There you go. So now you see here what is our IQR range. So somewhere, if this is 50-ish, somewhere like this is 50, the Q3 is like somewhere around 50, and Q1 is like somewhere around 10. So the IQR would be somewhere like Q3 minus Q1, that would be 50 minus 10, that would be 40, right? And the lower limit is 0, upper limit is 100. Lower limit is 0 because there's no negative runs, right? Like sehwag cannot hit negative runs. It's only positive, like either he hits runs or he doesn't hit runs. So min value is 0 and the maximum value it considered is 100. Beyond that, you see all these, there are outliers. So in some matches he hit like 250 or like 200 values, some 150 runs and something like that. So pretty extreme behavior. So that's quickly how you can see the IQR here, right? The median is this line over here, which is somewhere around, I think, 30-ish, somewhere like if this is 10, maybe this is 20, 25, 30, somewhere around 30, you can say. Now, how do we get it accurately? So we'll look at so we'll see how we can actually get the exact precise values. Give me a moment. Okay, so so the obviously now to find IQRs we need the quartiles, the percentiles, right? So let's find out. So the steps will be something like, what we'll take is we will get the 25th percentile. We will get the 50th percentile, although I don't think we need 50th one, but that's fine. We'll get the 75th percentile. Then what we will do is find the IQR. Find IQR. Then what we'll do? What are we trying to find? We are trying to find how consistent. We are trying to find. Yes, so I find the IQR, then we find the edges of the box plot. So we can find the edges of the box plot, which is our max value in this case, min and max values, right? Then we will try to find the number of outliers. Find number of outliers, and based on the outliers, we will know like what percent of total what percentage are the outliers in his data set, which will give us the his consistency score. When we compare it with the Rahul Dravid's outlier score, that is when we will know who is more consistent. Right? Let's proceed with these steps. So to find the 25th percentile, let's say P25, we use the np.percentile method, which let me see what does it take. Array like or real numbers, input array or object that can be converted to an array. Okay, so I think I can drop the dataset directly, which is say drop sehwag. Nope. Percentile missing one required positional argument q. Array like or float percentage or sequence of percentages for the. Okay. Yeah. So I mean, we didn't give it what percentile we want, right? So this should be 25th percentile. So the 25th percentile is around 8. So if you see here, yeah, we estimated 10, so it's pretty similar. Now let's go with 50th. This will be 50. So that's around 23. Yeah, we estimated around 25, so pretty close, 25. And then let's go for the 75th percentile, which is it should be around 50. (46). So these are our percentile values. Now we'll calculate IQR, which is 20 P75 minus P25. That is 38. So IQR is 38. So the range so the spread of sehwag's dataset is 38. Before that, let's look at the descriptive stats of sehwag. Sehwag.describe. So if you see here, the mean is 33. It's actually not too, which is that is a little strange because okay, wait 1 second. Dot sum by okay, so it is 33. Interesting. Okay, I guess I guess I guess there are a lot of data points. I guess that's why it there are 245 data points. Not that many. Yeah, but anyway, that's why even though the sum is so large, you see here there are 8273. If we look at the sum is 8273. If we look at the max value, the max is his max score is 219. So even though there are such vast outliers, since there are a decent number of data points, that somehow got the mean to be somewhere close to the IQR. But again, if the correct range in this case is still the IQR, which is 38. So 38 is the correct spread for sehwag. Now what we can do is, since we got the IQR, we can try to compute the max value. We'll do the min as well, since we can anyway. So min, let's do it. Min will be Q1, which is P25 minus, so if you remember, Q1 minus 1.5 times the IQR. So the min value here, this is irrelevant anyway, but float object is not callable. Oops, okay. Should be this way. So the min is negative 49, which is irrelevant. That is pointless, because you cannot have negative runs in cricket. So what we will do is we'll calculate the max value. Which is Q75. You remember Q3 plus 1.5 times IQR. So the max is 103. So you see here, about the same. Seems to be matching the data, right? So if we look at our descriptive stats as well, the max is 219. Okay, this max is different. This is not the IQR max. This is the max value of the data set. Is the min value of the data set. If you see here, the percentiles, we got it pretty correct. So 25th is 8, 50th is 23, and 75th is 46, right here. We'll calculate standard deviation. We already got calculated the mean anyway. So this is the max value. So how do we find out the outliers? So we want to, now in this data set, we want to find out all the runs that are greater than this 103. So all we have to do is, we'll use a mask, which is sehwag, which is greater than the max value. So these are all the points greater than the max value in the box plot, which is our, as you can see here, these are all greater. Now, all we have to do is, let's call them outliers. So all we have to do is calculate the percentage of outliers. So total outliers by total number of data points in this data set. This will give us so length of the outliers. This will give us around 0.57. So around 5.7% of the 5.7% of times sehwag seems to have hit crazy numbers, like crazy runs, like something beyond his expected what you can say. So beyond what is expected of him, he has hit 5.7, around 6% of times. Now let us calculate for Dravid. We'll have to do the exact same procedure. Let's import the Dravid dataset. So we have it here, right? We'll follow the exact same steps. So I will not spend too much time here. I'll just copy the exact commands as it is, just to save some time, because we'll have to do the cleaning for this as well, which we don't have to. So yeah, starting from here, we will do this, and the columns are also the same, so there's nothing fancy here. We'll be computing the exact same steps everywhere. Yeah, let me just take them. Oops. We will drop the labels, and I will copy them. I have the info. And replace. Yeah, then we will say Dravid this time is df runs. Oh, I did not I did not import the dataset. 1 second. This will be Dravid. Believe we have it. Yeah, there is dravid.csv, and yeah, then we will do a box plot as well. Yeah, let's do it till here, then we will see the remaining steps again. Now for Dravid, let's run it. So this is the, is this Dravid? No. This is sehwag. So this is the Dravid's box plot, right? If you look at side by side, so as you can see, the Q1 for Dravid is somewhere around, you can say it's around 10, and Q3 is around 58-ish somewhere, and the median is around 20, probably 25, 30 is somewhere over here, right? The min is obviously 0 and max is around 120. And there are very few outliers. As you can see right from the graph itself, you can tell there are only like 3 outliers here compared to like 3, 4, 5, 6, 7, 8, 9, like about like maybe more than 10 here. So that's our first initial observation. Now let's do a df.describe just to get our descriptive stats. So again, min is 0, max is around 153. Okay, so yeah, the outlier value is around 153. Yeah, let's follow the exact same procedures. I'm not going to go through all that. We will follow these same steps. $75 IQR. So then we will do a min and a max. One second. Did I copy it here? Okay, that's interesting. Why did I do it here? Wait. I think I mixed it up. P75. Okay, this is P25. This is P75. Outliers and right now we'll use the exact same thing. To get the percentage. Okay. So let's call this print string 25th percentile, P 50th percentile, then 75th percentile, then let's print the IQR as well, then Actually, let's keep it slightly differentiated so that no, I think when we compute standard deviation, I think that might cause issues. So what we will do, we'll first compute the standard deviation for I think it's np.std if I'm not wrong. Yes, that is np.standard deviation. We just pass the standard deviation of this value. So maybe if I just pass sehwag, nope. Okay, so we got the standard deviation as well. Nice. I don't think I have to do any more computation there. Yeah, we won't need variance here because standard deviation tells us what we need. In this case, this will be dravid. So this will be min then we will do for max as well. And we'll get the print the outliers as well. Hopefully I'm not messing up. Okay, I did not set it here. Yeah, so we are printing the outliers, then we will print the percentage as well. Print and the standard deviation. Okay, let's see. So what are these outliers? Is it? We have max is this one, and outliers. Okay, it's printing outliers. I don't think we need that. So total outliers are 3, just 3 of them, and outlier percentage is 0.9. Yeah, that's correct. Okay. So that was 0. It was 0.9. Oh, okay. Yeah. So as you can see here, let's do the same for sehwag as well. Print dravid. So we can see side by side the percentage. Sehwag. Oh, I don't think we can. Yeah, this will give us dravid's values because we are using the same we are using the same variable names. So okay, yeah, I should have done it in a different way. Okay, that's fine. We can compare anyway. So as you can see here, the outlier percentage is 0.9, which is less than 1%, right? While sehwag has around 5.7, around 6%. So from the outliers itself, we can tell that again the definition is the spread of the data set, right? The lesser the spread, the greater the accuracy. So in this case, we can conclude that as per this data sets, Dravid is the more consistent player compared to sehwag. And that's actually reflected in the standard deviation as well. The lower the standard deviation, the better. So if you see here, sehwag's standard deviation is around 34, while his is 29. Right? So that is how we can conclude this case study. Yeah, now let's that's all there is to this case study, and as you can see, this is quite useful. We can also, again, this is my like my favorite example is one of the favorite examples is this one. You can measure the performance. You can also measure the precision of instruments. Like if you have two machines and you want to know which one has the least error, like which one has the best fit for of these best, like which one, yeah, I mean which one has the least error, you could say. The one with the lower standard deviation or lower variance is the one that is more precise, right? And this is like very useful one, and and that is all there is to measures of variability. Now let's quickly look at the random variables, which is discrete and continuous random variables. We already saw something similar in the probability class about discrete and continuous spaces. The concept is the same, excepting in this case, random variable is nothing but any situation or an experiment or an event where the outcome cannot be predicted, right? That's why it's random. And in random variables as well, you have like two types, again discrete, it's called RV. You have discrete and continuous. So discrete is something like the best example is coin toss. It is something you can discrete means countable. Continuous means uncountable. Like you will have infinities within infinities, or you'll have infinities between any two numbers. So discrete random variables are integer based. Like you will know what is the next number. So suppose if I take 1, what is the next number? It's 2. Next number is 3, so on up to infinity. And you'll have negative infinity as well. While in continuous random variables, what is the next number of 1.1? Is it like 1.11? Is it 1.1112? Between 1.1 and 1.2, there's an infinity here, right? And between, if we say 1.11 and 11 and 1.112, there is another infinity here as well. So it's infinity of infinities, and you cannot. So basically that's the point. So to give you an example of discrete random variables, the best example is coin toss, right? what are the set of outcomes here? Like you will have head and a tail, right? Just two of them. You don't know which outcome it will be, but you most certainly know it will be within these two. You won't have outcomes beyond this if you properly define the experiment. If it is a fair, which is the unbiased means fair. If it's a fair two-sided coin toss, two-sided coin, then you will have only these two outcomes here. The same with the six-sided fair dice roll. I mean fair dice, right? The outcomes are basically 1, 2, 3, 4, 5, 6. That's it. So, well, okay. So these are some examples of discrete random variables. If we see continuous RVs, you will see like heights of people. Like some people can be 5'10", some people can be 6'3", 6'3.1", 6'3.2. The gap between 6 feet 3 inches and 6 feet 1 inches, you can have any number, right? Same with temperatures, right? If there is a temperature between 15 degrees and 15.3 degrees, you will have again an infinite here. The similar stuff. So that is about random variables. We'll look at this random variable thing in detail in distribution classes, probability distributions, and in the upcoming classes anyway. So this is just the basic theory. I hope that was clear, and yeah, I'll see you in the next one.